As Calder Hall began to deliver electricity to Britain's power grid in October 1956, history was made. The opening of the world's first full-scale atomic power station heralded the beginning of a new age. With a total of 4 reactors, Calder Hall A and B supply 150,000 kilowatts to the national grid. And at Chapel Cross, a similar twin station with 4 reactors was built. This too delivers an output of 150,000 kilowatts. But Calder Hall and Chapel Cross are operated by the United Kingdom Atomic Energy Authority primarily for plutonium production, at some loss of power output. With the increasing demand for electric power for industry and the home, not only in Great Britain but throughout the world, so grew the need for atomic stations specifically designed for power output. To assist in meeting this demand, 3 large organizations, English Electric, with worldwide experience of electrical power generation, Babcock and Wilcox, specialists in steam generation for 3/4 of a century, and Taylor Woodrow, civil engineers with a proud record at home and overseas, pooled their already valuable experience in the field of atomic power. More than 2 years before the opening of Calder Hall, English Electric had taken part in design studies for nuclear reactors for the Atomic Energy Authority. At Whetstone, near Leicester, a growing team of scientists, engineers and technicians had engaged in research and development aimed at improving the efficiency of the Calder Hall type of reactor and developing new designs. Babcock and Wilcox, backed by their research laboratories at Renfrew, had cooperated with the Atomic Energy Authorities as early as 1947 in the application of nuclear energy to the production of electric power and produced design studies for nuclear ship propulsion. It was they too who developed the thermodynamic cycle for Calder Hall and designed and constructed the entire steam raising plant both for Calder Hall and Chapel Cross. Taylor Woodrow, as the civil engineering contractors for Calder Hall, had also brought in valuable experience to the group. There they had faced and overcome many new and unusual problems, working to standards of accuracy far above normal. Yet they finished the work ahead of schedule, and many of the techniques they developed there have been adopted by others entering the field. The work of these organizations, now linked together as a team, gained momentum. They carried out advanced studies on graphite problems. New research rigs were built. New materials and new designs for fuel elements were examined using equipment operating at reactor temperatures. They investigated problems of corrosion of reactor materials and conducted exhaustive tests on the uranium fuel. Metallurgical, combustion and heat transfer research over a period of years produced for the group an enviable accumulation of knowledge and experience in nuclear technology. Site construction problems were also extensively studied, both in relation to building methods and to the transference to site of works experience in welding vessels up to 6 inches thick. Performance and design studies were facilitated by the extensive use of electronic computers. These included examples of the digital type, such as the deuce, and the analog computer. Backed by all this experience, the group developed an unsurpassed capacity for the design and construction of nuclear power stations of the gas-cooled, graphite-moderated type. Stations ranging from 30 megawatts up to the largest. The principles of a graphite-moderated, gas-cooled reactor can be described quite simply. In a pressure vessel, fuel elements containing rods of natural uranium are arranged in vertical columns in a core of graphite. Extra channels in the graphite core accommodate control rods, long tubes of boron steel. When the control rods are partially withdrawn from the core, a chain reaction starts and the fuel elements heat up. Carbon dioxide under pressure is blown through the core past the fuel elements, thus carrying away the heat. The whole is contained within thick concrete protective walls called the biological shield. The hot gas is now used to heat the tubing of steam raising units, so producing steam to drive the turbo generators. The cooled gas returns to the reactor and the process is continued in a closed circuit. But the permissible temperature of the fuel elements is not as high as the temperatures customary in modern coal or oil-fired furnaces. Consequently, the gas temperature is restricted. However, by making use of a dual-pressure steam cycle, designed and developed by Babcock and Wilcox, some of the gas heat can be used to raise steam at a relatively high pressure and temperature. The remainder of the heat is used to raise steam at a lower pressure and temperature. In this way, a considerable increase in thermal efficiency can be achieved. These steam conditions bring problems in turbine design. In low-pressure cylinders, the maximum blade size must be limited to keep blade stresses low. The English Electric Company drew on their long experience in turbine manufacture and met these special conditions. And so it was that the group was able to perfect a design for an atomic power station with an output nearly 7 times that of the original Calder Hall, less than 6 months after its opening. That station is Hinkley Point, the world's first 500,000 kilowatt atomic power station. Hinkley Point is notable for its compact layout and workmanlike appearance. The 2 tall buildings house the reactors with their 67-foot steel spheres inside thick walls of concrete. Connected to each reactor, there are 6 steam raising units, 3 on each side, and the buildings below house the gas circulators. The charging floor is equipped with specially designed machines for refueling without closing down the reactor. The graphite core consists of columns of interlocking bricks and tiles with channels for the fuel elements and control rods. The gas ducting to the steam raising units is more than 6 feet in diameter. At the other side of the reactor buildings are housed the monitoring mechanisms and other instruments for control and safety. Each of these buildings is served by a storage pond into which spent fuel elements are discharged to reduce their radiation. The turbine house has 6 generators, each of 93.5 megawatts, supplying the supergrid, and 3 variable speed 33 megawatt generators to power the gas circulators and other equipment. Overall control is exercised from a central control room with a system that assures maximum safety and reliability of operation. At one end of the turbine house there are workshops, the administration block, canteen, and welfare buildings. The station is located as near to the sea as possible to bring it within easy reach of the large volume of cooling water needed. It is in fact partly built on reclaimed land enclosed by a sea wall. To design such an atomic power station is one thing, to construct it efficiently, economically, and to schedule may be quite another. Hinkley Point is located in rural Somerset. The few roads in the district were mere country lanes, and none of them led all the way to the site, nor were they suitable for the traffic that would be necessary. The nearest possible point for offloading waterborne equipment was at Cummich, 5 miles away. But the tidal range is up to 40 feet, and much construction work would be needed to make it serviceable. At the site itself, as a preliminary to foundation design, soil exploration had to be undertaken. To explore the seabed adjacent to the necessary cooling water tunnels, offshore rigs were used. Then the Somerset County Council authorised the construction of a suitable access road, and Taylor Woodrow got to work, clearing and levelling, straightening and widening the old lanes, making bypasses, and laying a new section right through to the site. In all, they constructed 6 miles of access road in under 6 months, making the way easy for two-way traffic and the transport of heavy and bulky loads. Now the job could go ahead, and heavy earth-moving equipment was soon at work in all weathers on site clearing, levelling and excavation. Excavations for the reactor foundations and all other work were carried out to a strict schedule, planned months in advance. The sea wall had to be built to enclose a large area of foreshore. This could only be done between tides, but while concreting was in progress at one point, sound planning ensured that no time was lost elsewhere. Along the line of the wall, seawater was pumped away for the erection of the next set of bays. At Cummich, the tiny creek echoed to the sound of pile driving, as a wharf was built to handle heavy loads to come by sea from factories at Renfrew, Liverpool and elsewhere. On the site, the ground was prepared for the reactor pressure vessel foundations. The entire pressure vessel, core and support structure, weighing 5,500 tons, are borne on a ring of 1 3/4 inch steel, 30 feet in diameter. The foundations were designed for a pressure of 10 tons per square foot. Concrete for all the work was mixed at a central batching plant, erected as soon as the ground was ready. The load on the foundations for the biological shield, the reactor's concrete housing, 7 feet thick and 90 feet high, was even heavier than for the pressure vessel. These foundations were constructed in alternate bays to reduce shrinkage and in lifts of 5 feet, using concrete either pumped from the central plant or brought in skips. To speed the work of handling the reinforcement steel and the heavy shuttering, 2 travelling ground derricks were employed from the beginning. This followed the Taylor Woodrow practice of saving costly time by the early and generous use of mechanical aids. Good progress was made on the sea wall, and work soon began on sinking the access shaft for the cooling water tunnels. At high tides, the sea was still flooding the area to be reclaimed for the turbine house and the cooling water plant. But the work of filling went on unchecked. Work on the first reactor building was now well on the way. The primary shield enclosing the spherical reactor was made 12-sided to simplify construction. And this in turn was surrounded by a rectangular secondary shield to enclose the ducting and other equipment leading from the reactor vessel. To give protection from radiation, concrete of high standard and uniform density was needed and was thoroughly compacted. Strain gauges were built into the primary shield as a permanent check on its stress resistance, and the shield began to rise quickly from foundation level. While this work went on at increasing pace, the 3,000 feet long sweep of the sea wall was completed. Within the area reclaimed from the Bristol Channel, excavations began for the 700 feet long turbine house and for the deep foundations for the cooling water pumping machinery. Nearby, a huge caisson was under construction in a dry dock at the water's edge. This was to be sunk a third of a mile from the shore as the intake for the cooling water. A large area was set aside for workshops and fabrication. The reactor and steam-raising unit vessels were far too big to be transported from distant factories. They had to be fabricated in fully equipped workshops on the site. The shops were also to be used for work on the gas ducting, core support grids, steam pipes, and other items of Babcock manufacture. This was indeed a case of bringing the factory to the site, and it called for the exercise of good administration to look after the comfort and well-being of the workers employed on this great undertaking. The labor force at times exceeded 2,000, and fleets of buses were used to transport men to towns and villages scattered over a 20-mile radius. Many others were accommodated in a well-found camp adjoining the site, laid out with the object of providing more than a mere place to sleep. Within the boundaries of the camp were a church, post office, hairdresser, outfitter, and other shops. After the day's work, a man could come back to his own quarters, drop his heavy working clothes, and put his feet up if he liked, or relax in a variety of ways in the recreation center, just as he wished. Progress was all the time being made on the construction of No. 1 reactor building's biological shields, now nearly 90 feet high. In the turbine house area, the extensive foundation work included preparing the reinforcement for the heavy blocks to support the turbines and generators. Over at Cummich, the wharf was finished and the first shipment was unloaded. This consisted of prefabricated parts for a large Goliath crane. The crane was assembled and erected on the site to be used for lifting heavy loads into the reactor buildings. The same coordinated planning extended also to the factories of the group. At the Babcock works at Renfrew and Dalmuir, work was already underway. The rings for the steam-raising units were fabricated from steel plates of up to 2 3/8 inch thickness. These were assembled and longitudinally welded at the works before shipment. The heavy grid to support the graphite core was also fabricated here, and the segments of the reactor pressure vessel, in some cases with gas ducting outlets attached, were welded up into larger assemblies before dispatch. This centralized planning applied equally to the English Electric Works at Stafford, Rugby, and Netherton, where the turbine house equipment was in production, including the stator cores for the main generators. These were more than 7 feet in diameter. The air blast circuit breakers for the switchgear serving the supergrid, and the air pressure control panels associated with them. In the newly built factory at Whetstone, English Electric began to produce the graphite blocks needed for the reactor cores. Here they were machined to shape, bored to make the channels through which the fuel cans would pass, milled with keyways so that they should interlock accurately and fit exactly in their predetermined places in the core. After each block had been produced, It was automatically inspected on a machine registering every dimension simultaneously. The work of an hour or more reduced to 1 minute. Back on the site, the foundations for the pump house machinery were progressing on schedule. The cooling water requirements of the turbine house plant are 35 million gallons of seawater per hour, which explains the impressive dimensions of the work. The biological shield for #1 reactor was now up to its full 90 feet. And in the turbine house area, the turbine blocks were well advanced. The cooling water outlet culverts were constructed within a large sea cofferdam. And in the dry dock, the intake caisson was almost ready for floating out. Cumich had been a busy place in the days when the Romans ruled Britain. Now, once again, it sprang to life, serving the needs of an industry far removed from those of ancient times, as it received the rings for the steam-raising units and other material arriving by sea. Now the factory on the site moved into top gear. The reactor pressure vessel plates were assembled here and welded together into courses before being placed in the biological shield. Temperatures in this shop were strictly controlled. Continuous preheating was used. Circularity was maintained by making all welds in each course simultaneously. And all welds were, of course, to Class 1 standard. In another shop, the steam-raising unit shells were assembled and welded. These vessels are 90 feet long and 21 feet in diameter. On a suitable high tide, the 4,000-ton caisson was towed from the dock to its appointed resting place out at sea. To make contact with the 1,800 feet long cooling water tunnels being driven under the seabed, it was necessary to ground the structure within 6 feet. In fact, it was lowered into position only 10 inches from its mark. Both reactor buildings were now well advanced. #2, with its 12-sided primary shield, at the full height of 90 feet, and the secondary shield almost finished. At the same time, in #1 building, a thermal shield was being installed. This consisted of steel-reinforced concrete slabs spaced from the wall by an air gap, through which cooling air will be blown. In the fabrication shop, finished welds were X-rayed to confirm that they fully met the highest standard specifications. This applied to every inch of every weld on every pressure vessel. While the charging floor walls were being built on #1 reactor, the turbine house had reached the point where steelwork was being erected. The gas circulator buildings for the first reactor were also under construction. A further stage in the production of steam-raising units was stress relieving. This was done by induction heating with the induction coils suitably insulated. An essential aid to the construction program was the 400-ton Goliath crane, largest of its kind in the world. When the welding of the skirt ring and first 2 courses of the reactor had been completed, this crane was used to lift the assembly from the fabrication shop, sharing the load of nearly 300 tons between 2 crabs, each of 200 tons capacity. 250 feet high and 250 feet wide, the crane was supported on 4 rail bogies with interlocked driving mechanisms. Its height allowed it to straddle the full height of each reactor building. With this unique crane in use, the amount of work needed inside the biological shields could be much reduced. Erection problems were simplified, and more than 6 months construction time was saved. Delivery of the first courses of the pressure vessel marked a significant stage in production. The first step in erecting the first reactor vessel in the world's first 500,000 kilowatt atomic power station. But progress was also being made in other directions. In the compound set aside for the switchgear, structural work had already begun. The offshore caisson was now linked to the land by a cableway. The fabrication of the steam-raising units had reached the point where the first was almost ready for lifting after its hydraulic test. At the workshop end of the turbine house, steel work had now neared completion, and a start was made on roofing and cladding. Then came the biggest load for the Goliath crane, the first of the 12 steam raising units. Towering over the shop where it was fabricated, its 90 feet length and 385 tons total weight were handled smoothly and accurately by the giant crane as it made its journey from the fabrication area to its appointed place on #1 reactor.